In continuation of my lecture on entropy, today I shall try to formulate the entropy change of different reversible processes. And you know, I have already told in my last lecture, entropy is a very important property in thermodynamics. It is like a sun in planetary system. And the sun, the first letter S may be given to this to symbolize the entropy of the system. So the various thermodynamical properties are related with the entropy of the system. And I shall try to first build up the two important relations between entropy and internal energy, and entropy with this enthalpy. Internal energy and enthalpy have been discussed fully in the first law of thermodynamics. Now, the relation between first the entropy S and internal energy. Of the system. Internal energy U of the system. And we know from this first law of thermodynamics, that Q reversible, if the process has been assumed reversible, then it will be the internal energy change of the system plus a PdV. PdV is the mechanical work done by the system. So this second law, at the same time second law states that a Q reversible by temperature is equal to the entropy change of this system. So this Q reversible equal to TdS. It is the entropy change of the system between the two states at a temperature T. And you all know that the absolute value of entropy could not be determined by the use of the second law of thermodynamics. It could only be evaluated by this use of this third law. Entropy change we can determine. Entropy change is like this internal energy change in adiabatic work done. So this TdS, if we equate this one and this one, then it is obviously coming this TdS equal to du plus PdV, or this du equal to TdS and minus PdV. And this is the relation between the internal energy change of the system with this entropy change of the system, and dV the volume change. And this is the equation number 1. This is a very important equation, and we call the basic thermodynamic equations. In total we have these 4 thermodynamic basic equations, and this is 1. And so I can write here this du equal to TdS and minus PdV. This is equation number 1. Then another, this relation between entropy and enthalpy. I can build up very simply. H is equal to U plus PV. Or you can say dH equal to du plus PdV plus VdV when no restriction has been made for this differentiation. And you see this du plus PdV is equal to TdS. So this one equal to TdS, or you can say dH equal to TdS and plus VdP. This is another basic thermodynamic equations. So this is given equation number 2. So this equation number 1 and 2, these are very important, and later I will formulate another 2 basic thermodynamic equations. So this one I can write here, this dH equal to TdS and plus VdP, and this is equation number 2. And by the use of these 2 equations, we can formulate the expressions for the entropy change in different reversible processes. Today I shall only discuss the reversible process for ideal gas, for say 1 mole ideal gas. This is our discussion, and this entropic change we can determine with the help of these 2 equations. We know that du, the change in internal energy, is equal to CVdT for 1 mole of this gas, for 1 mole ideal gas. And Cv is the molar heat capacity at constant volume. So instead of writing this du, we can have the CVdT equal to TdS and minus PdV. And so for this we can replace this P equal to RT by V for this 1 mole of ideal gas. So this one actually TdS and minus RT and dP by V, or ds equal to ds equal to Cv dt by T and minus R plus R dV by V. So this is the differential form of this entropy change in terms of this temperature and volume change, and Cv is the molar heat capacity at constant volume, and R is the universal gas constant. This we can write here, this ds equal to Cv dt by T and plus R and dV by V. This is another equations. We are writing these equations so side by side in this left. So integrating, if we assume Cv is assumed to be independent of temperature, if we consider independent of T, and we do the integrations, then this is ds, here S1, S2, these two are the limit. S1 is the entropy of this initial state, S2 is the entropy of the final state, and Cv is taken out of this integration as it is independent of T, and here it is dt by T, and here T1 and T2, these are the limit. And plus R will also go outside of this integration, dV by V, and here V1 and V2. And the change of state of the system is like this, T1 and V1, and it is going to T2 and V2. These two are this is the initial state, this is the final state. We like to get the entropy change of these two states. So this one, whenever integrated, S1, S2, and it is equal to del S. And del S equal to Cv ln T2 by T1 and plus R ln V2 by V1. So this equation is very important. If you know this initial temperature volume, final temperature volume, you can calculate this entropy change for the system between the two states. And so this one we can also write this del S equal to Cv ln T2 by T1 and plus R ln V2 by V1. We have assumed that Cv is independent of temperature. So if we use this second equation, then in a similar fashion we can write instead of dH, we write this Cp dt for 1 mole ideal gas. And so here Cp dt equal to TdS and TdS plus VdP. Or say ds equal to Cp dt by Cp and dt by T, Cp dt by T and minus V by T and dP. But for ideal gas, PV equal to RT for 1 mole. So V by T, you can write this R by P. So you can write R by P instead of this one. So this ds equal to Cp and dt by T and minus R dP by P. This is also another form here. Write ds equal to Cp and dt by T and minus R dP by P. And this is another equation. So these are the different forms of this entropic change in different processes. And whenever we do integration, keeping this Cp independent of temperature, then it will be similar way, del S equal to Cp ln T2 by T1 and minus R ln P2 by P1. For the change of state, for the change of state of the system, here T1, P1 and going to T2 and P2. And this will be the entropy change for these two states. Cp is the molar heat capacity at constant pressure. Cp is assumed to be independent of temperature. So this one also I can write here, del S equal to Cp ln T2 by T1 and minus R ln V2 by V1. These equations are to be memorized to solve this problem more easily in this examination hall. And here if the reversible, if the process is reversible isochoric or say isobaric, reversible isobaric, then P1 equal to P2, then del S equal to Cp ln T2 by T1 for 1 mole of this gas. If the isothermal process or say reversible isothermal process, then T1 equal to T2 and this one equal to 1, so del S equal to minus R ln P2 by P1. And similarly for this case, if it is reversible isochoric, that means V1 equal to V2, then del S equal to Cv ln T2 by T1. T2 by T1, and this one will be equal to 0. So reversible isothermal process, then T1 equal to T2, and so this formula becomes del S equal to R ln V2 by V1. It is obvious that whenever the temperature is constant, isothermal process for ideal gas P1 and V1 equal to P2 V2, and so P2 by P1 equal to V1 by P2 by P1 equal to V2 by V1 equal to P2 by P1. That means V2 by V1 equal to P1 by V2. And here is negative sign, and this will be like this. So these are the formula deduced on the basis of these two equations. These are the very important equations. These two are called the basic thermodynamic equations. Now I like to determine the entropy change for this reversible phase change. Reversible phase change means this substance moves from one state to another. The reversible phase change, or before that I like to determine this reversible adiabatic process for 1 mole ideal gas. And we know the reversible adiabatic process is isentropic process. So this one, if we put this one, then delta S equal to 0, and this will be Cv ln T2 by T1 and plus R ln V2 by V1 for the change of state T1 V1 to T2 V2 for in a reversible adiabatic process. Reversible adiabatic process for this state of change. This process is called the isentropic process, so delta S equal to 0. So from this relation we can conclude several features for this process. One is that these two terms. This is the first term, this is the second term, and sum of the two terms is equal to 0. Means one term is equal to the other terms in magnitude but opposite in sign. Means the entropy change due to the volume, the temperature change compensates the entropy change due to the volume change for this change of states of the system in this reversible adiabatic process. So we can write also this the R ln V2 by V1 equal to minus CV ln T2 by T1. Or you can write, if you remove this minus, then it is T1 by T2. So this equation, from this equation we can infer, say for reversible adiabatic process, adiabatic expansion. So let us take the reversible adiabatic expansion. V2 is greater than V1. V2 is greater than V1. So this term is positive. This side is positive. Then right hand side must also be positive. Then if it would be positive, CV is positive always, then T1 must be greater than T2. What it concludes, or we can get an idea that in case of reversible adiabatic expansion, there is a fall in temperature. Final temperature is less than the initial temperature, means the temperature falls. So for reversible adiabatic compression, opposite event or phenomena will occur. That means for reversible adiabatic compression, there will be a rise in temperature. So another thing is that R by CV, if we divide by CV, then it is equal to n into ln V2 by V1, and this is equal to ln T1 by T2. Or you write ln V2 by V1 whole to the power R by CV is equal to ln T1 by T2. If we cancel this ln from the both sides, then V2 by V1 and to the power R by CV equal to T1 by T2. So, but R by CV equal to for ideal gas, R equal to Cp minus Cv by Cv equal to Cp by Cv minus 1 equal to gamma minus 1. Gamma is the molar heat capacity ratio. So in this case, this relation leads to T1 and V1 to the power gamma minus 1 equal to T2 and V2 to the power gamma minus 1. So this is the relations between temperature and volume for this ideal gas in a reversible adiabatic process. Another thing is that I like to remember that this relation, whenever we have integrated this relation or this relation, whenever integrated, this Cp has been taken independent of temperature. But whenever the Cp depends on temperature, in that case, what will happen? Then we know that in that case, Cp you cannot take it outside of the integration. So ds integration S1 S2, and this one will be equal to integration Cp and dt by T and T1 T2 and minus R and dP by phi. But if we assume this Cp is dependent on temperature, dependent on temperature, then Cp could be expressed with the temperature in a power series, as I have done in case of a Kirchhoff equation. So Cp, we can write as Cp equal to A plus Bt plus Ct square plus dot dot. A, B, C, these are the virial coefficients. These are the characteristic constants of the substance. And these A, B, C, they could be evaluated by means of experiments. So instead of writing this Cp, instead of taking out the Cp of this integration, we can write this on left hand side is del S and right hand side is T1 and T2, and instead of Cp we can write A plus Bt plus Ct square plus dot dot into dt by t, and this one minus R dp by p, and this one also dp by p, and here p1 and p2. So if we do the integration, then a dt by t, and this is the limit, so it will be a ln t2 by t1, and this side tt cancels, so plus b into only dt remains, and whenever integrating, this will be t2 minus t1 plus this one, 1t will cancels, so c by 2, and this will be t2 square minus t1 square. This is the up to the temperature variation. This is the temperature variation, and minus r ln P2 by P1. This is for the pressure variation. So whenever this Cp depends on temperature and Cp varies with the temperature in this power series or virial form, then this del S, and to be changed for these two states, we can write in this way. A, B, C, these are the virial coefficients, could be determined by means of experiments. Now I am coming to the phase change, reversible phase change. A reversible phase change or phase transition of a substance. And reversible phase change of a substance, this is also sometimes called the first order phase transitions. And suppose one example is that say it is 1 mole ice at 0 degrees centigrade and 1 atmosphere pressure, and it gives 1 mole ice, 1 mole water, and this temperature, same temperature, 0 degrees centigrade and 1 atmosphere. So the water remains in two phases. One is solid and another is liquid, and solid-liquid phase transition occurs at a given temperature and pressure. So long the pressure remains fixed, the temperature will also remain unchanged. As this system, you can say this system, it is water, and this is suppose the ice and water remaining in equilibrium under 1 atmosphere pressure. So this system, actually this system is the two-phasic system. So phase rule, F equal to degree of freedom equal to C minus P plus 2, and this is only one component, water. So 1 and 2 phases are there in equilibrium. These 2 phases are in equilibrium. So minus 2 and plus 2 equal to 1. That means pressure, temperature, concentration, or only 1 degree of freedom, one parameter you can vary independently according to your own choice. Here, if you keep this pressure fixed, then temperature will automatically fixed. If you suppose the temperature temperature is slightly increased, is temperature temperature is slightly increased from 0 degrees centigrade, and 1 atmosphere pressure remains the same. Whenever the temperature slightly increased from this 0 degree centigrade, the temperature will not change so long these two are remaining in equilibrium. What happens whenever the temperature is increased? The ice will melt down. Ice will melt down, and this whole system will contain only the water. Whole system contains water only. And if the temperature is decreased, if is slightly decreased, very small, slightly decreased from 0 degree centigrade, and 1 atmosphere pressure remaining same, then again also the temperature will not change so long these two are remaining in equilibrium. In that case, whenever the temperature is tried to be decreased, all this water will form this ice. Then the system contains only the ice only and no water. So this is the reversible process, and also occurring at constant temperature. And the entropy change of this process, equal to the heat change by temperature, and this is the reversible heat change, Q reversible by temperature. Here this temperature, this heat is not going to increase this temperature. It is not the sensible heat, it is the latent heat. Latent heat used to change the phase of this substance. And the heat supplied, here heat is to be supplied, it is the endothermic process. So this heat change at constant pressure is called the enthalpy change. And this is the transition, so enthalpy change for this transition, divided by the temperature at which the transition occurs. So in this case, if we consider, then this one equal to, for 1 mole ice to water, the heat to be given up, and this heat approximately say 6,004 joule mole inverse, and divided by the temperature 273 Kelvin, or a temperature 2700 Kelvin. So this one almost gives the 22 joule Kelvin inverse and mole inverse. This is the entropy change for this phase change of water from ice to water. You can see this one is positive. That means S2 is greater than S1, means randomness increases whenever the ice is melting down to water. Randomness of this water is being increased. So for other cases, suppose other cases of this phase change, suppose for this freezing, this is delta S, freezing, it is melting, or it may be called fusion. It is freezing, and to be changed in this freezing process, this will be del H, and it is freezing. Enthalpy change for this 1 mole of freezing, and this one is the temperature of this freezing. And this freezing process is exothermic process, so there will be minus sign. So in case of boiling, delta S vaporization, this will be also equal to delta H B boiling, or delta H vaporization, and this it is the boiling temperature. So now the another thing in a reversal process, I like to calculate the entropy change of the universe for a reversible process. So long I have discussed the entropy change of the system. Now it is the entropy change of this universe. So it is very simple in this case. If you consider, suppose this is the system, and this is the surrounding. So if you supply this amount of heat, say suppose Q, in a reversible process at a constant temperature, both these two are at constant temperature. In that fashion, you are supplying this Q reversible from the surrounding to system, and this could be done if you increase this volume slightly, very simple way, infinitesimally, then the temperature falls, and to maintain the same temperature, constant temperature, heat will be flowing from this surrounding to this system to keep this temperature fixed. So this type of process I have shown in Carnot engine during the derivations of the efficiency of this Carnot engine. So in that case, the del S system gains this energy, so Q reversible, and this temperature T at constant T, and this del S surrounding, this one is losing this heat, so minus Q reversible by T, and so del S universe total equal to del S system plus del S surrounding. So this two equal to Q reversible by T and minus Q reversible by T, and this is equal to 0. But it could be shown in better way. So the entropy change here also write the entropy change of this universe equal to 0 for a reversible process. Whenever the process occurs reversibly, at every step, you know the reversible processes contains infinite number of steps, and in each step the system attains equilibrium. So this one equal to 0 for reversible process, and also this is the condition for equilibrium, condition of the equilibrium of the system. Actually, whenever the process attains equilibrium, the entropy change of this universe is also equal to 0. This could be shown in better way by using this Carnot engine. Actually, Carnot engine is very popular for getting these different complicated concepts in a simple way. Suppose this is the H tier and temperature T, and here the engine or the cycle, here Q amount of heat is given to this engine, and this is some part of this heat is converting into work and work done, and this is the L tier are this temperature T dash, and here Q dash amount of heat is given thrown to this LTL or this heat sink. So this is the Carnot cycle. So this is the universe, and this universe outside of this boundary there is no interactions. So this universe contains the system. Engine is itself a system, and engine works in a cyclic fashion, and these two are the surroundings with which the engine is being interacting. So this del S system system means del S engine. Del S engine, and this one equal to 0 means engine is cyclic fashion, and so entropy is a state function. For any state function, the entropy change in this cyclic process is always equal to 0. So del S surrounding equal to del S HTR. This is one part, and del S LTR. And this one equal to HTR loses this amount of heat. So minus Q, and this temperature at which it heat transfer occurs, and in this case LTR acquires this heat, that means plus Q dash by T dash. And we know from this Carnot cycle efficiency equal to 1 minus Q dash by Q, and this is also equal to 1 minus T dash by T whenever both are the Carnot engine. So in that case, this Q dash by Q equal to T dash by T, or Q by T equal to Q dash by T dash. This has been shown in several times in our last lectures. So this one and this one are same but opposite in sign, so this will be equal to 0. So in this case, it is nicely shown that the entropy change of this universe, so entropy change of this universe equal to del S system plus del S surrounding, and this one equal to 0 plus this one also equal to 0, so this is equal to 0. So the same conclusion we are having from the concept of this Carnot engine, and it is the most important condition for the reversibility of a process. Problem, I like to give one problem based on these equations, and this problem is that show that isobaric temperature coefficient of entropy means del S by del T at constant pressure is greater than isochoric temperature coefficient of entropy del S by del T at constant volume, and plot S versus T curves using ideal gas for the reversible isothermal, reversible adiabatic, reversible isobaric, and reversible isochoric processes. And this is the curve S versus T. And for this first one, the reversible isothermal, the means entropy will be increasing and temperature remains constant. Temperature remains constant, entropy is increasing, so this will go like this way, in this upward direction, so vertical. And in this case, reversible adiabatic process is isentropic process, means the entropy remains the same, but there will be change in temperature. If the adiabatic compression, so then temperature will also increase. So this curve will be like this, parallel to this t-axis. And for this reversible isobaric process, we have to search here reversible isobaric process. It is this one. This one isobaric process means dp isobaric inside of this 3 isobaric for isobaric process dp is equal to 0, so this term will vanish. So del S by del T at constant pressure, this will be equal to Cp by T. So this curve S versus T curve is positive. This one is positive. That means with the rise in temperature, this S will also increase. But the increase of this S with the T means it is the slope. The slope is a function of a T. with the increase of t, slope is decreasing. Means with the increase of t, slope is decreasing. That means it will be a curvature, and this curvature is naturally the negative curvature. Negative curvature means slope is positive. Slope is positive, and curvature is negative. So fourth case, this is the isochoric process. In case of isochoric process, this one dV equal to 0 for isochoric process, dV equal to 0. So this term will vanish. So del S by del T. So this del S by del T, temperature coefficient of entropy at constant volume, this will be equal to Cv by T. Since Cp is greater than Cv, Cp is greater than Cv, as you know, for this ideal gas, Cp minus Cv equal to R. So as this slope of this S versus T for this isochoric process is smaller than this one. That means for this isochoric process, it will be like this. With the rise in, this one is also positive, the slope is positive, means with the rise in temperature in this isochoric process, entropy will increase, but the slope will be this one. The slope here also, slope will be equal to positive, and curvature is negative, as the slope is decreasing with this temperature. If we like to determine this curvature, then actually we shall have to do this del 2S by del T square at a constant pressure. So in this case it will be minus Cp by T square, and this one is negative. This is the curvature, magnitude of this curvature in this isobaric process. So this is negative, means it will be increasing with the rising temperature. Its increase is slow. And similarly del 2 by del S by del T square at constant volume, this one will be equal to minus Cv by T square. So in this case also, the curvature, this is curvature. Curvature means the slope of the slope. This is also negative. So these three curves are drawn, S versus T plot, and this is the isothermal, increasing vertically, adiabatic, it is horizontal with this T axis, parallel to T axis, and these two are increasing, but isobaric change of entropy with the temperature is greater than this isochoric change of entropy with this temperature. So this is all about these reversible processes, and in my next class I shall discuss the entropy change for this irreversible processes. You know, the irreversible process is the real process, and it is spontaneous process, so it will be to some extent complicated. In my next class I shall discuss the entropy change of these irreversible processes. At the same time, I like to prove the Clausius inequality, and the entropy change of this universe in irreversible process. So that's all. Thank you all who are watching this video. If you like, then please subscribe.